Welcome everyone to the 2023 Photonics Spectra Spectroscopy Conference. Thank you all so much for joining us, and in this session you will hear from John Gilmore, the Spectrometer Business Development Manager at Hamamatsu. John works on the development of application-specific inspection equipment and is joining us today to discuss key considerations when you're working with Libs. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any sort of technical issues throughout this event, please log out and back in to rejoin the session. John, we appreciate you taking the time to present at the 2023 Photonics Spectra Spectroscopy Conference.
Okay, thank you, Jacob, for that introduction, and welcome everyone. Yes, my name is John Gilmore, and I am the Business Development Manager for Spectroscopy Solutions here at Hamamatsu. And I'm pleased to be discussing with you today the laser-induced breakdown technology. During today's talk, we'll break it down into these different categories. First, I'd like to explain what is laser-induced breakdown spectroscopy, or commonly referred to as Libs. We'll talk about a key aspect of the application, which is the formation of the plasma. We'll look at the excited states of the plasma and their dynamic emissions. And that'll lead us into some of the individual components of a Libs system, as well as applications of Libs technology and a look forward. So what is Libs? As I mentioned, Libs stands for laser-induced breakdown spectroscopy. As shown on the left here is a diagram of a typical Libs system. And it's important to note that Libs is part of the atomic emission spectroscopy kind of family of applications. And I'll talk more about that in the next couple of slides. It's been around a while. It was first introduced by Breach and Cross back in 1962. Basically, the technique involves using a laser to excite a sample, creating a plasma, and that plasma emission is detected through a spectrometer or some sort of optical detector. The plasma, as shown in the diagram on the right here, the plasma, the laser excitation can really cause saturation in a lot of detectors, and it's important to be able to gate the detector, or it's important to be able to gate that on during certain timing windows, as the spectral information is really contained in different segments of that time. And we'll look more at those details as we go through. So Libs is becoming really popular because it doesn't require any handling sample preparation. It's really a nice point and shoot type of application. Within the Libs community, it's referred to as a non-destructive method, but we'll see as we go through some examples, the laser does cause some micro scale surface damage. So some people look at that and say, well, why is it referred to as non-destructive when it does cause a finite amount of damage to the sample? But again, that's just kind of how the community refers to it. The other benefit of Libs is that it's real time and you get a lot of information. We'll look more in details at that spectral information, but just shown in the diagram here is a Libs spectra. And you can see associated with that spectra are many, many emission lines from various atoms or molecules that are contained in the sample that's being measured. And although the initial Libs systems were laboratory benchtop, we'll also look at examples of Libs today, which is really a portable cordless drill size implementation. I know this is kind of a busy slide, but I wanted to take the time to talk about, in the center is the so-called Jablonski diagram, which is associated to the physical chemistry of the technique. The excitation on the left here, we have a typical illustration of an atom with the proton and neutrons in the center and electrons circling the atom in their outer orbits. As whatever the form of excitation may be, whether it is from a spark, from an inductively coupled plasma, from a flame, there's a lot of means of exciting the atoms and causing these electrons to go from their virtual ground state to an excited state, as shown here in the Jablonski diagram. At some point, those electrons are going to want to transition back to their lower ground state, and when they do so, they also emit a photon. The energy of that photon and its wavelength are exactly dependent on the energy between these transitional states. And that is how one can capture the material content that's associated with the Libs measurement. So there's lots of examples of atomic emission spectroscopy, as I mentioned, such as flame and spark or ICP, and there's probably several others. But what really sets Libs apart from these other techniques? And the one thing is that it's a single step, the excitation of the sample with the laser and the detector. The laser is only on for a few nanoseconds, and the optical signal is fed back to the detector within a matter of nanoseconds, hundreds or thousands of nanoseconds sort of timescale. So it's really pretty instantaneous. Just to reiterate, as I mentioned earlier, it doesn't need any sample preparation, so it's really quite easy to use, and you get a lot of information. You have this simultaneously detecting multiple species of atoms within a given sample. So those are really the things in my mind that helps to set Libs apart from the other techniques. You can see the citations that Libs is gaining. The numbers are growing quite significantly because there's advances in the laser and spectrometer technology that are allowing Libs to be much more portable, reliable, and handheld implementations. With the tremendous amount of data that's generated from a single Libs spectrum, the other advancement in chemometrics and artificial intelligence for pattern recognition are really a vital part of the growing popularity of a Libs system. So now let's look at one of the key aspects of Libs technology, which is the formation of the plasma. And when we look at the formation of the plasma, we can really break it down into these 4 steps. We have the laser that is interacting with this surface of the sample, and as it's releasing atoms off of the surface of the sample, it's ionizing those atoms, and it begins with the excited states of those atoms, it begins to form a plasma. As the laser continues to excite the sample, more and more atoms are generated, and it's kind of, this is where the plasma, the hot plasma is formed here, and this is where the term of breakdown occurs, as the atoms are kind of breaking down with electrons being excited to the higher energy states before the final phase of the plasma, which is as it starts to cool. And we'll look more carefully at the different aspects of a cooling plasma. But as the plasma starts to cool, when those, remember back to the Jablonski diagram, when those electrons in their excited states transition to lower energies, they give off photons of various energies, photons of various wavelengths. And that is the information that one needs in order to identify the materials. We looked at the formation of the plasma. I've talked a lot about these excited states, and I think that this series of illustrations really helps to visualize what's occurring. So the spectral here is a time wavelength plot. So the gating of the detector, as I mentioned earlier, as the plasma is cooling, we want to be able to select a particular time window in the plasma in order to gain the proper spectral information. So you can see that at 50 nanoseconds after the laser pulse, there is really this continuum of fluorescence signal. It doesn't have the spectral lines and the unique features, but 150 nanoseconds, 300 nanoseconds, as that plasma is cooling, those atomic emission, those electrons are making those transitions from their higher energy state to a lower energy state, giving off photons, and that photon emission is all represented in these distinguished peaks in a Libs measurement. Shown here on the right is another illustration of the same concept, where we can see that you have the laser pulse that is producing the formation of the plasma. And once the laser pulse turns off, we want to be able to gate the detector, in most cases a spectrometer. We want to be able to gate the spectrometer to detect these ionic lines. Remember in the previous diagram, we saw that at 50 nanoseconds, it was just kind of this continuum spectra without the emission lines, because that's exactly what is occurring in the plasma in the beginning. So it goes through this continuum emission, some ionic line emission, but then we get into the real part of the measurement, which are the atomic lines. And during that window is where we want to gate the spectrometer on. All of the other signal that's collected in the spectrometer needs to be eliminated. So we'll look at different techniques of this gating. I mentioned earlier as well that the Libs spectra is very rich. So you can see here there are many different examples of atoms that are measured within a single Libs spectra. So what are some of the key components of a Libs system? So we looked at the formation of the plasma and the creation of photons as the plasma is cooling. So photon detection, and every photon is containing certain information, and every photon really is important and needs to be counted. So in our detectors, we want to look for detectors that have high quantum efficiency, which is the detector's ability to convert photons into electrons or photoelectrons. And we want to make sure that the detector is gateable. One common detector is a image intensifier coupled to a CCD camera. These are made by various manufacturers such as Andor, Hamamatsu, Horiba, and many others. They're really nice because they can be gated at very high speeds and have a very good extinguishing ratio as the device is gated off and on. But they can be susceptible to overexposure damage from too much light, and they require a high voltage to operate. So the incoming photons are converted into photoelectrons by a photocathode material. And there's a couple of different materials shown on the right here that are typical. And then the microchannel plates amplify those photoelectrons, and that's where the high voltage power supply comes in. And in the center here, we can see what a typical intensified CCD or CMOS camera might look like. More recently, and advancing the technology to be more portable, are solid state detectors. The photon detection, it's still very important to have high quantum efficiency. Every photon counts, every photon contains information, but solid state detectors such as charge coupled devices or CMOS image sensors are really dominating the handheld market these days. We'll look at one example of a so-called resistive gate charge coupled device and how it gates the accumulation of signal from the Libs. So in the example shown on the left here, after the laser pulse has occurred, we want to be able to get all of the signal out of the detector and prepare the detector for the incoming gated window of operation. So these characteristics are very important in a Libs-based detector and a Libs-based spectrometer. This is an illustration of a typical resistive gate CCD. The blue section is the active area of the CCD, and that's where the photons are going to be converted into electrons. Those electrons are transferred down into a storage gate region, and there's two key timing signals that the user has control over, which are the all reset gate, the ARG, and the all reset drain, the ARD. By controlling these two timing signals, we can essentially dump the excess charge that's generated from unwanted signal, such as the bright laser pulse or the continuum emission that we saw earlier. We can keep the CCD in this sort of reset or cleared state until we want to gate it on to collect the atomic emission spectrum. So that CCD would be placed in a spectrometer of sorts. This is a typical illustration of what a spectrometer is and what it does. So the incoming light from the plasma essentially goes through some collimating lens and a dispersive element such as a transmission grating. And then that spectrum is imaged onto a CCD or CMOS detector with supporting electronics to enable this spectrometer to be gated in the appropriate time window. These spectrometers have very high optical throughput because every photon counts. They generally would have a USB computer interface or some means of collecting the data to a microcontroller. And they're kind of replacing the high-end image intensifiers in Libs applications. And it's important as well that the spectrometer have very good optical resolution, and that would be its ability to distinguish between neighboring peaks. We saw in previous slides how rich the Libs spectra is, and that there are many, many analytical lines closely coupled to each other, and one needs to have a spectrometer that has adequate optical resolution in order to be able to resolve those lines. So those are all of the key considerations when selecting a spectrometer. You want to make sure that it covers the wavelength range you need, has the optical resolution needed, and most importantly, can be gated in the appropriate time window. Another key component of a Libs implementation is a high power laser. That laser is going to be a critical component in the formation of the plasma. So things to look for when selecting a laser is the pulse timing. Generally, the nanosecond pulsed laser is pretty common on the market because in the nanosecond timescale, the formation of the plasma is really dominated by the thermal effects that the laser is delivering. If you go to a femtosecond laser, then it's the formation of the plasma is really a non-thermal process and can be a little bit more difficult to manage. You want to be, there's a table of specifications from a typical solid state laser that is emitting at 1064 nanometer, and it shows like the energy in the pulse, the wavelengths, and the number of pulses that the laser can produce. So having looked at the different aspects of a Libs system, we can now look at some applications and future implementations for Libs. We saw earlier the vast increase in the citations of Libs in a general way, and these graphs are showing a more specific publications for some specific applications. Applications such as coal, metals, water, soil, food, biomedicine, all of these different applications, and how rapidly the inquiries or publications for Libs technology are growing these days. I mentioned earlier, these sorts of, I think this one is made by a company called SciAps, but there are many other vendors making similar products. This is not an endorsement of any one over the other, but more to just show by illustration, what these handheld Libs instruments look like. And as you can see from the pictures, it's really just, there's no special sample handling, there's no special sample preparation. It's just a matter of pointing and shooting. So inside of this Libs instrument are all of the key components that we broke down throughout the webinar. You have the laser diode to form the plasma on the surface of your sample. You have collection optics to bring the optical signal back to the spectrometer, and the gating electronics and software to gate the spectrometer on during the appropriate emission window. Some more applications and places that one can find Libs technology. Kind of a fun fact, Libs is on Mars, so the rovers in space exploration use a Libs spectrometer. It can also be used in many other applications, ranging from pharmaceutical, biomedical applications, environmental, and so on and so forth, as illustrated here. The non-destructive aspect of it does draw into a little bit of controversy with some of the applications, such as ancient art, using Libs to analyze ancient art. It can leave a very small amount of surface damage. So that would probably be of consideration. And finally, a future outlook and some of the things that I think you're going to hear in other talks throughout the morning session here. One of the applications that seems to be growing in popularity is inline inspection. Because of the high-powered lasers are getting more efficient. we're able to move the sample and the detector a bit further apart, and Libs could be used for inline inspection of some produce or samples, substances coming past it on a conveyor belt. So look for Libs in some of the in future applications of inline inspection. You'll also hear about the use of Libs for detecting fluoride in medicine type applications, in bones and teeth. Energy and the nuclear reactor designs use Libs technology, lithium-ion battery inspection, and rubber inspection. These are all additional areas where Libs technology is being implemented. And that brings me to the end of my talk. So I want to thank everyone for your attention, and thanks for signing up today.
Thank you, John, for joining us and highlighting key considerations when implementing Libs. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 2023 Photonics Spectra Spectroscopy Conference. Thank you all so much for joining us.